Hi, good morning, and welcome on this first session of AU here in Vegas. And also good morning, good afternoon, or good evening for the people that are watching this presentation online. This is about generative design and how we are going to apply this in the AEC industry. And my name is Dieter Vermeulen. I'm working as a technical specialist at Autodesk. And covering everything around computational design and engineering in the Northern European region. I'm based in Belgium, and I'm very passionate about generative design. So it's actually partly my job, partly a passion, a hobby. So that's really nice if you can combine that. I'm doing this already for more than 5 years now at Autodesk, and my previous experience is actually structural engineering. And this comes in very handy, which you will see when I go through a few of these examples, to have a little bit of that background, at least to have a little bit of analytical mindset to approach some of the problems. Now, through this presentation, I'm going to showcase lots of examples that are going from design automation to computational modeling to generative design. And I'm going to explain you all of the processes and at least give you some overview in these processes and how they are composed to each other. But first, I would like to give you a little bit of background on why we are talking about generative design. And one of the things is, of course, demographic changes. You've heard that story probably already a few times, but by 2050, we expect to have like a lot of people on this globe, 10 billion. That's the estimation. Meaning that the number of cities, they will double. And we will need to build about 13 building units per day to make sure that all of these people have houses. It means that we need to build more than 3,600 extra building units per day as what we do today now. This means that we have a few challenges. A challenge of having to do more, and that's inevitable. And at the same time, there is also less resources, less people, less talented skills. That's a reality. If we combine these two things with each other, we have an opportunity of doing better. I'm pretty sure that when we are all going to the main stage keynotes after this one, we will hear way more about this better. Now, and also another thing is the designs today. How do we look at designs now? Actually, there is not that big difference if we compare it with the way how we designed buildings 50 years ago, except for that we now use computers. But actually, the expertise is still in our heads. It's still humans that decide how a design will look like, how a design will be made. Now imagine if we combine this with computational power. Then we have way more options to look at these designs. Now in a traditional design process, it's like a game of battleship. You blindly guess on a spot if you're doing any kind of simulation or analysis, and you can wait for a hit or miss, or having a miss answer to come back. Now, by the time you get a hit, you're willing to settle for the acceptable solution instead of leveraging a larger design space and getting closer to the optimal solution. While in a generative design process, it's someone who makes a concept, defines the constraints and goals, and then use a computer to generate all kinds of solutions, evolve those solutions, and use those algorithms. These are kind of things we don't have in our brain. We cannot achieve that very quickly. And then again, it's someone, it's a human again, that's evaluating these options. Evaluating, refining them, and selecting the right solution. So it's not that battleship game anymore. It's really about having better informed design decisions. Now, generative design is not just a tool or a software, it's more a methodology and a process. And that's something you need to keep in mind when you go through the rest of this presentation. It's a methodology, process. It's not like, let's buy generative design. And if we look at the growth in the AEC technology throughout the decades, we started with the era of documentation, where we were documenting ideas, where people put ideas on a piece of paper to explain how something needs to be built. With the introduction of BIM, we came into the era of optimization, where we are more talking about models, systems, where we create not only just like a 3D model, but also add data to it to express how a building should behave, for instance. But now we are in the middle of this era of connection. An era of connection is actually where we talk about data, the connection of data, and also the interconnection of that data with models, and connection with people. So it's about people combining with computers and creating specific designs with that. Generative design is a part of this era of connection. Now, in architecture, generative design is actually most applicable, we would say, which is not true, but that's something we focus on a lot. And in this class, it's also mainly about architecture, but I will still show you other examples in engineering and construction too. But now to explain a little bit, one of the challenges that comes up in a lot of these generative design conversations is that we need a stadium which is really optimal for everyone sitting in there. So we want people, or at least if we, all of us, are sitting in a stadium, we want to have like the best spot and not like this is better than the other. No, everything should be great. That's something that generative design can solve in this case. Or another very simple case could be a parking lot, and I want to feed as many parking spaces as I can in a way that streamlines the process of parking your car. Or another example is a medical facility, and I want to place an X number of rooms, and at the same time place them in such a way that, for example, the nurse can move from point A to point B in the fastest possible way. The last example can be in manufacturing. Say you're looking at a very wavy surface, and you want to figure out what should be the size of the tiles along that surface, so that I don't get a ton of little tiny slivers. And I want to minimize that amount of waste that I have and make it as easy as I can to construct it. So, during the presentation, we are going through several phases. I call it design technology progression. And at a certain stage, you will think like, okay, this is where I am, or this is where we are as a company or as a team. Keep that in mind. And from that point, you will know where you can go throughout a further evolution in your design technology. You will understand then, or at least be able to identify at what stage of that design technology progression you are right now, which means that you will also know how you can move up. So keep that part into mind. These are a few of the examples. So I'm going to showcase a conceptual tower mass where we want to use like a little bit of architectural rules to optimize the placement of that building, do some structural optimization. Let's have a look on what can be done in generative design with that. Also a little case about light distribution in the MEP industry. Construction with tower crane positioning, and then some urban planning and a parking layout optimization. Now, first stage of that design progression is traditional design. One thing in traditional design is sketching. I hope you're not all saying now, okay, this is where we are right now. And if we look at how people worked in the Middle Ages, for instance, to design buildings, you see those at the left-hand side, that building with those little crosses. If one of these crosses change, the rest of the geometry will change with it as well. Well, at that time, they had to redesign everything if some of these elements changed, and they have to restart over on the paper, of course. So that's where computer-aided drafting came in very handy, where, for instance, products like AutoCAD help us to design or to use sketching in a way, better way, and in such a way that you can, of course, delete easily your lines if you want to make changes to your model. So let's quickly go to another phase, because I expect most of you are at least at this stage. And this is about parametric design. So parametric design is about the human expertise, as I mentioned before already at the start of the presentation. And that person, he gets a computer to build a design, to create a design. But at some point, it's still a limited design, because you already have the idea inside of your head, and you document it onto your computer. You use a computer to explain how the idea that you have inside of your head will look like. And that's a bit limited in this case. Now, a technology within parametric design is parametric modeling. Parametric modeling is where we make implicit relationships and maintain them as you model. So these relationships between parameters gives us the possibility to create new geometries. That's typical for parametric modeling. If we take that conceptual tower, this is a workflow how it could look like in parametric modeling. It's using Revit, where we create a geometry, assign some constraints to it, parametric constraints, modify its parameters, and then document the ID with schedules, with plans, with 3D views, whatever. So let's take this project. It's about a building that we want to set up in the middle of a city. In this case, it's in Lower Manhattan in New York. And there are some rules to make that design. We need to have like an amount of plaza area in front of the building. The building cannot exceed a specific height. And at the other hand, we need to reach a specific FAR, floor to area ratio. And think about the number of floors it should have. What could be the revenue of that building for the owner? What would be the cost for the contractor? We cannot see this in parametric modeling. But what we can do in here is to make that building a little bit flexible, to make it easier to modify, so make it adaptable to changes. But other than that, we don't see those ROI values, the FAR, the number of floors. I cannot see it in one blink. So that's something we can optimize maybe. So let's go a stage higher. Still within parametric design, there is design automation. Design automation is where we take a few elements as input. We create some kind of an intelligence behind it to automate the way how they are placed into a design, and then you get your output. That's what design automation is doing. It's not only about modeling. It could also be about automating the way how you annotate your designs, how you create schedules, for instance, in a Revit model. So we have multiple solutions for that. There is Revit, where we have already quite some power, and the more power you get in the product, the more difficult it is to execute. And then still we have also the Revit API, and it even gives us more power inside of that software, and it helps us to create our own tools, but it's a bit hard because you need to program. So that's where Dynamo comes in very handy into that ecosystem. Dynamo will help us to have still more powerful tools, but in an easier way. It's easier to perform that. And this is a nice example of that. I'm pretty sure that people among you that don't understand what Dynamo is or don't know what Dynamo does, I'm pretty sure that you will understand what the right-hand side is doing. And if you don't, let me explain to you. It's selecting a model element, and it's asking what is the volume of that element. And the volume is like about 2.6 cubic meter, whatever. At the left-hand side, this is what you need to do as a programmer to have the same result. I will not explain it because I don't even understand it. So it's easy for someone who can program, and it's way more powerful because you can modify everything, every little action in your tool. At the right-hand side, it's more predefined for you. It's like a library of a little bit of content you get, and you can combine them together to make something logical. Okay, so what can we do with that on that building, on that conceptual tower mass? So instead of starting the design in Revit and creating walls and floors, we can use a specific script which is built in Dynamo by someone in the company who has an expertise in that. and the other people in the company who don't want to dig into Dynamo, they just want to use it. Well, they can have Dynamo Player for that. In this case, we already get some values from it, because we get like an evaluation: what is the total area, what is the FAR of that building, how many floors do we have in there, and use Dynamo Player to automate the placement of that building onto that given site. Now, this is built in such a way that you can also use it in a generic solution. So if the site would be, for instance, another city with a completely different perimeter, that would work as well. Or what about if I want to create more buildings on the same site? We can reuse that tool. That's actually what design automation is doing. Make something that processes your input and returns an output. And in the next example, this is something I received from one of our customers in Denmark, a company called AB Clausen. And these guys saw already the opportunity with design automation with Dynamo Player some time ago to do a very simple task, actually. The task in here is to have to create the openings in a structural model based on the openings in a linked architectural model. Instead of having to draw all of them one by one, they select all the walls from the structural model, which is happening in here, and it detects the openings in the architectural model and places the structural openings in the same structural model, just in a few clicks. That's done, like in 30 seconds. Okay, it took them maybe a week or a few days to build up the script, but in 30 seconds, they have this done on every type of building. Another case of design automation could be in the MEP industry. And this is about the placement of lights. It's a very typical example. There are lots of them available through the internet. So I use this example, something we received from Radu. And what we do in here is placing these light elements on a specific grid. So within Dynamo, you can select your parameters, select how it should be distributed along that surface, along that ceiling, and it takes into account all the obstacles, such as walls or maybe other transversal walls, to make sure that there are not any lights placed at that position. Now in this case, think about these light positions now. Is this actually an ideal position? Probably not. We can still tweak it. We can still drag those sliders in the Dynamo script and have another configuration, but I don't get any information about what is the light intensity inside of that room. Is it okay or not? What is the price actually to make these lights happening like this? So that's something we can keep in mind when we go through the progression of that design technology. Next example is about facade panels. I explained this case 2 years ago at EU in a class about design automation for architectural panels. And this is a case where the architect wants to place these elements on a complex surface in an automatic way, and at the same time get feedback on the fabrication details for these things. So is it even possible to fabricate them? Because if you have a facade panel on a double curved surface, sometimes you might have like a panel which has a plane deviation. So it's a bit like a torsion effect that is created on that panel. That's very difficult to fabricate. The guy that needs to manufacture that, he's like, oh, no, I'm not going to. He will not want to go on a Monday morning to his job for doing that. So it's good if an architect already can tackle this issue before it's even developed. So that's where Dynamo Player comes in very handy. At the same time, I also want to add some aesthetic elements to it. So we want to create that sine wave effect on those panels. So imagine that you have to do this in a manual way. That would mean that you have to select each of those panels and then change all of their unique parameters to have that sine wave. And then you probably will have an estimation. If the main architect then suddenly says like, hey, I don't like that sine wave, I want the amplitude to change a little bit, yeah, then You can start over again and do those 1400 panels again. So I prefer that Dynamo player and then just drag some sliders and done. That's design automation. Let's go a stage further. Stage further is computational modeling. It's still within parametric design. Now, the process in computational modeling is a little bit more complex. We take data as our input. It could be data, it could be geometrical data, it could be numeric data. And from that, we generate something, generate a model that can be analyzed. That's the extra thing we have in here if we compare it with design automation. It's the analyze part. Now, analysis doesn't necessarily have to be structural analysis or very complex engineering stuff. Analysis could also be what is the surface of that floor. That's already an analysis algorithm that you're making. Now, once we have analyzed that design, we can explore it, which means that do I agree with the results of it? Am I happy with the results? And if yes, then you integrate it into your design model. That's the whole process. Starting with data, generate it, analyze it, explore if it's okay, and then integrate it into your BIM model, for instance. So let's go back to our tower again, because I already had those results in my Dynamo player, but now I want to do way more about it. I want to see lots of these results. I want to analyze this design and see if it's meeting the local government requirements. Now, all of these examples, by the way, are available on a Dropbox folder. So if you go through the handout, you will find for each of these examples, you will find the scripts and the Revit model, so you can test it yourself as well. And within each of those elements, within each of those scripts, you will also find lots of descriptions on why it's done like that and what you should do and how it reacts and so on. So the script is also the manual. Now, in the meantime, as you could see in here, we can use those sliders to change the design, to change the geometry of it. And at the same time, within that pink group, we get the results of it. The results for the FAR, the results for the total area, the number of floors, and so on. And you can add as many of those outputs as you want. If you, for instance, also want to add these so-called watch nodes for the cost of the building, or the revenue of that building, or maybe the energy consumption of that building, it's up to you. You can make your own analysis thing in there. And lots of people within the Dynamo community already created all these kinds of so-called packages that contain analysis tools to perform way more complex things. Okay, let's go back to our light distribution. So as I told you, we just place those light elements, but we don't have any idea of the intensity of it. So in this workflow, we are getting the Revit context again, which are the floors, the walls, and the ceiling, and generate an option for the light placement, and then see what is actually that option doing, analyze it, and then evaluate it, evaluation or exploration. So it's not my idea, so I want to give credit to Jared and to Radu, who actually started building this script, and yeah, I've plugged it into a few more other packages to make this a little bit working better. Now, what we are actually doing here is selecting a context for placing the elements, which is the ceiling, of course, and the floor is our analysis surface. So we want to know what is actually this grid of lights doing or what is the effect, at least, of that grid of lights on our floor. And then use some tools to colorize the results. Green is okay, blue is actually unlit points, and red is overlit points. So you can play with the intensity of the lights, the power of the lights, and then see what is actually the effect on the floors. Now, this is a conceptual analysis. It's not like an exact science. It's more an approach on what will it be. The moment we want to have more detailed results on it, you need to use specific analysis tools to do that. But at least it gives us an idea if we have the right number of lights or if we should change that. Let's go into an example in the structural engineering industry. It's also an example that I used a few years ago here at AU and showcased at the Dynamo Design Slam. And this one is about a structural diagrid in steel, which is composed of multiple prefabricated elements. Now, we all know if you want to use standard steel sections, we have like a specific stock length, 12 meter or 16 meter, and we need to cut pieces from that stock length. Now, at the end of cutting your pieces from it, you always have like some part left, which is your waste. And in this case, we want to reduce the waste that we have when building this. So how can you reduce that? Well, to make your elements longer or shorter so that they fit in perfectly within a 12-meter stock length, for instance. So it's actually playing a little bit with the parameters of that diagrid, making the grid a little bit more dense or make it a bit more coarse, and using that specific way of designing that diagrid helps us really to find a good solution with less waste. It's not telling us anything about the strength of that structure. That's another analysis, but we could combine both of them. Structural analysis with the waste analysis, and maybe also with some other analysis for constructability, or even some analysis things for the cost of that building. So you could combine all of it in one script together. Now, the integration part in here is where the model gets created in our Revit model, and at the same time, we also get a schedule telling us which elements should be taken from which stock length. So you get your fabrication details in your structural engineering model at the same time. So that's a bit design automation combined with that computational model. So you get a bit of all flavors into these kinds of workflows. So we had traditional design with sketching. We had parametric design with parametric modeling, design automation, and computational modeling. I'm pretty sure that some of you will already have an idea. Yes, this is where we are right now, right? Okay, how can we progress then? That's the next step. This is about generative design. Now, this is the most exciting part, actually, of the presentation. So lots of exciting examples. It's still about that human. So generative design is not replacing humans. It's not like we are all going to lose our jobs because of generative design. No, we need that human expertise. Someone needs to say how that algorithm should work. Someone needs to build a computer to make this working. Someone needs to work with that computer. So it's that human with computational algorithms and a computer, and this results into lots of design options. Hundreds, thousands, millions of design options in the same time as you would need to only describe one in a traditional or parametric design method. So think about that. That's actually a lot. Try to do 1,000 design options in a manual way. It takes you forever in your project, right? And generative design is something that mimics the nature's evolutionary approach. And designers or engineers, they input design goals into some generative design software along with parameters such as materials, manufacturing methods, or cost constraints. So it's like the theory of Darwin inside of a computer. So we as humans, we evolve as well, as you could see. Now we are like a little bit struggling in how are we evolving? Are we going to do sitting work or standing work or using touchscreens or not? Now, within that process of generative design, we add a few more steps. So we already had the data, the inputs that generates a model, and then we analyzed it, and we used explore behind that step. Now, within generative design, there is also a ranking in there and an evolve part. Now, I'm going to explain you each of these steps one by one. First, generate. So generate is the stage when design options are created or generated by the system. That's using algorithms and parameters that are specified by the designer. In the analyze part, it's where the designs are generated in the previous steps. They are now measured, or they are analyzed on how well they achieve goals that are defined by the designer. You hear? Defined by the designer. So it's the human, it's the person that defines how this should work. In the ranking phase, which is that new part in it, comparing to computational modeling, ranking is based on the results of the analysis, and the design options are then sorted in some kind of way. They are ranked. We put them on like, oh, this is my best one, this is my second best one, this could be my third best one solution. And evolve is an extra process on top of that ranking. Within evolve, the process will use the ranking of the design options to figure out in which direction the designs should be further developed or evolved. And that's where these algorithms, these genetic algorithms are used. That's where the theory of Darwin, let's say, the evolutionary theory, evolve, of course, is used in here. Now, I can explain way more about these genetic algorithms, but it's going to drift us away from the topic. It's a very complex thing, and there is lots of information that can be found within the links that I've placed in the handout. So in there you can find lots of information on how these genetic algorithms actually work. So the next step in that process is then explore again. Now, explore is where the generated designs are compared or explored by the designer. So again, it's the person coming in here, and it's inspecting both the geometry and the evaluation results. Once we found our champion, we can integrate it into our design model. So this is the window which is fitting within that building, according to our constraints, according to the goals we want to achieve with it. So a product that last year already was announced at this AU here in Vegas is Project Refinery. And Project Refinery is a public beta project for generative design, meaning that every one of you can access it. You can access it through that link and play it with it yourself, but you have to keep in mind it's a beta. But it's a really exciting thing, this Project Refinery, because it's actually, learning the interface is actually taking you a few seconds. The only thing you need to learn is to change your mindset, as I told you, and learn about the generative design process. And that's the most difficult part. So it's not that difficult to run Refinery on a Dynamo script. No, it's to know how should I analyze a building, how should I deal with those constraints of that building, how should I deal with goals, how should I even set goals for my designs. Now, a few of the studies, or generation methods as we call them as well, within Refinery are explained here. The easiest one is randomize. Randomize is actually where we are taking a random number of inputs for these, or values at least, for each of the parameters, combine them and create a design space with it. So the design space is actually the number of design options you have in there, and they are ranked according to your parameter values and the results you have for them. So in this case, the outcome could be 5 designs, and we use them to evaluate which are actually my most optimal one. Within cross-product, we do more or less the same, but instead of a randomized selection of your values for your parameters, it's more structured. For instance, for parameter 1, I want to have like 5 different values, and 3 for parameter 2, and then combine all of them with each other. So A with 1, B with 1, C with 1, A with 2, B with 2, C with 2, and so on and so on. And you get like 15 designs. Now, in both of these studies, we don't know if our perfect solution or the ideal solution, I don't like to say perfect, it's the ideal solution, is it actually in that design space? It could be somewhere in the middle, somewhere in between that nicely structured array of design options for the cross-product one, or somewhere between those 5 elements within the randomized study. So that's where optimize can come in very handy. Within optimize, we generate a combination of parameters, values, and evaluate it. And that's actually where that genetic algorithm comes in. It's evaluating what is actually the result. And if I'm happy with it, then I can evolve it, right? It's evolving into a next generation. And that one is evolved again into a third generation, a fourth, a fifth, a sixth, until it's converging into one perfect solution, one ideal solution. And another study is what we call like this. Like this is actually more to refine a little bit your solutions. Could be that you found a solution which is very close to what you want to achieve, but you want to see what would happen if I change it a little bit around that one single point. Okay, within generative design, there is again some kind of stages. First stage within generative design is actually option generation. And option generation is where we use that randomize or cross-product type of study. And we use that to actually skip the evolve part. Why would we skip that evolve part? Well, of course, within designs or optimization of designs, you don't always need to use that genetic algorithm method. You can also use a very randomized way to have very quickly a set of solutions to evaluate it. So that's actually where option generation comes in very handy. Designs that doesn't need to be very accurate, or you want to use option generation just to use a computer to generate IDs because it's Monday morning, you don't know where to start. Okay, let's use option generation. So what about if we apply this on a conceptual tower? On our same project within Lower Manhattan? Well, actually in this case we are reusing that script that was built. And we are reusing it to run that randomization on it. So within randomize, within refinery here, we are going to say that each of these parameters should be evolved in, not evolved, should be generated in a random way. So take that parameter of, for instance, the plaza position and the plaza offset and create a number of options. And this way we get like a whole set, 50 options in here that are evaluated at the same time. And we can use the outputs, the enhanced outputs within refinery to create an evaluation of it, to rank them actually within that coordinate system that you have in here, that parallel result system. Or you can use the thumbnails to evaluate its geometry. Or we have that 4D scattered diagram that we just saw with those little circles colorized and positioned in the right order. So this helps us to find now the ideal solution for it in some kind of a way. And this way it helps us to define the right parameter context. So it's actually not generating the most ideal solution, it's generating a few solutions. And this way, you can, as a user, you can find out, okay, these parameters, within that range, we can use these values to optimize the whole thing. It will become clearer a bit further in the presentation. Another example where randomization or option generation comes in very handy is crane positioning. We don't need to optimize the position of a crane with an accuracy of 1 millimeter, of course. So randomization is a very quick solution for it. At least if we generate enough options, we can use that options to evaluate what is the best placement of that tower crane. So the workflow in here is where we already have our design model. So we are going to evaluate an existing Revit model. So we are not going to generate geometry. We are going to evaluate a geometry to place new elements. So the existing building, a precast building in this case, is one of the inputs. The site where actually the cranes can be positioned is another input. And the delivery position for the trucks is our third input. Now these cranes are then positioned, again, together with the trucks, just in a random way. And the script is evaluating if every of these elements can be lifted from the truck and can be delivered on the construction site at its right position. When it's green, then it's okay. When it's red, it's not okay. Or when it's orange and yellow, it's somewhere in between and it might need some extra attention to make it working. So when you build those kinds of scripts yourself, it's always good to make a flow chart of it. And this is, for instance, the flow chart for this little script. So it's actually not that big. We could extend that flow chart with lots more of if this, then that solutions. But this is already enough to understand how the script works, or at least for yourself to know how to build up that script. So as you can see, we have the three inputs: the context of the elements, the context for the crane, the context for the trucks. We analyze them, combine them together, and then see what is happening if we compare it with actually the load capacity and the range of each of these tower cranes. So let's see how that works in that scripted environment. So again, Refinery in here is taking the script that is already exported to Refinery from within Dynamo. As you can see, Refinery runs from within Revit, meaning that we can use this way to select a context in our existing Revit environment and run that optimization script on top of it. So Refinery is, in this case, opening up a few sessions of Dynamo at the same time. So it's like a parallel process, a headless Dynamo, so you cannot see it. It's not running in the foreground. And it's generating all of these options, taking the results of it, and then showcases it within the Refinery user interface. Again, with the thumbnails, the 4D scatter diagram, and then also with the parallel results system. Now in here, I already see very quickly what is actually liftable and what isn't. So, but within that parallel system, we can use a filter to only select the solutions with the maximum percentage of liftable elements. And as you will see in here, it's not a perfect solution. There are still some elements in orange or in yellow, meaning that I might need a local solution to make these elements positioned in the right spot. Or maybe it could even help if the truck is just coming a little bit closer to the crane. These are very obvious solutions that you can have for it. But using that's actually the value of it. By using this script, by using this way of approaching the cranes, you can easily see if it's possible to use these types of cranes that you have, or if you have to go somewhere else and find new cranes and rent new cranes, or even buy new cranes for making this working. So this is helping you easily to see if less obvious solutions are also possible to work in here. So that was option generation. Let's go to the ultimate level now within generative design, which is in here design optimization. And design optimization is, again, that same process as we just saw, but it's now using the evolve part in it. It's going to use the genetic algorithms to find an ideal solution. And again, for that tower, we reuse that script again. Actually, what you didn't see is that throughout the whole presentation, it's one and the same script used for each of the design progression examples. It's only used in a different way. So the script in here is exported to Refinery. And again, Refinery is opened up in Revit to select the context, which is actually the parameter of the site. And this is then evaluated. So we evaluate that context to generate a building on it. And the parameter values for the plaza offset, for the plaza position, they are evolved in such a way that we are finding results which are way more optimal than what we would have in an option generation process. So we get 4 or 5 solutions in here. And each of these solutions are reaching those specific goals. The goals, as you could see at the start of the movie, start of the film in here, not movie, but the film, is this. We want to, for instance, maximize the total area maximize the facade area. We want to only have solutions with an appropriate FAR and so on. So that's actually the difference between option generation and design optimization. You define your goals. You say what should be maximized and what should be minimized. Another example could be, for instance, minimize the cost of the building and maximize the revenue of the building. These kinds of things. Another example is light distribution optimization. So we've placed those lights. We didn't know if they were placed in the right way so that we could have like less unlit points and less overlit points. We tried to do it with computational modeling to see what is actually the result of my solution. Now within design optimization, we are not going to drag the sliders manually anymore. Now we are going to use Refinery to optimize their position. So again, it's reusing that same script that we've built within the computational model stage. But now it's again used by Refinery. So it's every time the same process. You take the Dynamo script, export it to Refinery, open it up in Refinery, and run it. So the most difficult part in here is not clicking those check boxes and define what should be maximized or minimized. No, the most difficult part is actually making your analyze process within your Dynamo script. That's always the thing you have to think about when you start building these kinds of scripts, for instance. So in here, the analysis within Dynamo is taking all of these points and it's evaluating its race, and it looks at what is actually the distance between the point on the ceiling and its analyzes point on the floor, looks for the length of that ray and the intensity of the rays, and that's used to evaluate the light intensity in the full room. Now again, within Refinery, it's generating all of these solutions, but with design optimization, it's starting with a random solution set, and then the second generation is evolving the parameters in the right direction. So it's actually dragging those sliders into the right position until it converts into the best solution for it, until it actually reaches that goal. Reaches the goal for a minimal amount of unlit points and a minimal amount of overlit points. That's actually what I want to achieve in here. Another one within the structural engineering is a spatial truss optimization. That's an example that already was showcased at AU London together with the guy that developed DynaShape, Long. And we've used DynaShape at that moment to find perform a conceptual analysis of that truss. So it's not an exact science. It's using relaxation theory to find the shape that a spatial truss would take when it's having a specific overhang, when it's having a specific width and length. And within that workflow, the geometry is defined within Dynamo. It's using that DynaShape package to analyze its deformation, and then we get results from it. What are the results? Well, very simple. What is the deformation score? What is the material score? And what is the platform area? Now, what is a score in this case? A scoring system is where you use a specific unitless value to identify if your design is good or bad. So for instance, a deformation score in here could be like if the distance is a very exaggerated amount, then I want to have a deformation score of, for instance, 1,000. If the deformation is 0, then I want my score to be 0 as well. Or maybe you want to allow a little bit of deformation, because otherwise your structure would be like too much of material in it. So you could also say, like, if deformation is 0, then my score is like minus something. At the same time, you're also evaluating the material, because I want to avoid having a structure which is too heavy or which is like over-designed, because of course we can create trusses with the maximum amount of material and nothing will happen. It will not even move if a truck is placed on it. Yeah, then you have like an over-designed truss, of course. So that's where material score comes in to make it working, that you have like a reasonable amount of material in there. So scoring systems is something you can define yourself. It's really something that you use as an engineer or as an architect or a contractor to say like, this is how I want to evaluate my design. I give it points. 10 points for the best solution, 0 points for the worst solution, something like that. Now, how does that work then in a practical example in here? So this is an overview of that script used in there. And a good thing, a good practice actually, if you build up those scripts, is that you use colors for your groups. Use colors for what is input, use colors for your generate part, use another color for your analyze part, and then for your evaluation part. And this way, you can identify yourself very easily which part of my script is evaluating the thing, and where can I modify it to, for instance, change my scoring system within my solution in here. Now, this is still it's an old video. The interface of Refinery changed since then, but it's still using the same technology and it's still showcasing actually the same possibilities. Now, in here, of course, we want to minimize the material score and minimize the deformation score, but at the same time, I want to have the biggest platform ever. So you get like a contradiction, having something with less deformation, but which is really big. And that's where optimization comes in very handy again, because it will find like that ideal middle point between minimum deformation, minimum material, maximum amount of platform area. Now, within that scatter diagram, you get this curved results actually in here. It's that what we call the Pareto front, and meaning that all the points that are actually on that curve, all of them are like some kind of an ideal solution. Ideal in such way that, for instance, in one case we have a maximum platform area with less material, and in another one we have a maximum platform area with less deformation, but not the three combined with each other. So sometimes you might have this in what we call a multi-objective optimization. The trick in there is then to make sure that your scoring system is built that way that it's like some kind of a weighted value. So it's up to you to define then what is most important in here, the deformation or the material, and you weight those scores. And within Refinery, it helps you to filter then your scores and to have like a design space which is smaller to choose from, instead of having to choose between 1,000 options. So that's a danger you have behind these generative design solutions, that you might generate a really big bunch of solutions, but you don't know which is now the good one for you, right? So make sure that doesn't happen. Now let's go into an example of one of our customers in the Netherlands. It's a customer called Stamhuis, and besides the fact that it's about a liquor store, they used generative design to optimize that liquor store. So what I want to do in here is define within an existing building what should be the ideal placement of the shelves and the counter, what should be the ideal size of the storage area compared to the shop area, to have a shop which has like a big revenue, right? That's always the goal for everyone who owns a shop. They want to have the biggest revenue. But in this case, it might help to change the position of these shelves and at the same time evaluate that design to see if the counter is placed in a good position, for instance, concerning security. So the owner of the shop, he wants to see all of he wants to have like a full overview on his shop. He wants to see what is happening in my shop. Are people taking bottles maybe with them without paying them, for instance? Now, this is done within Refinery again, resulting in a few solutions where each of those solutions has its properties in terms of being ideal. And then again, it's up to the user, to the designer, to evaluate, to refine its selection, and to see what is actually the solution that I want to have in here, which goal is actually the most important in here. It's still a concept, but it's going to be developed way more, so keep an eye on that. You will hear more about this exciting workflow in the very near future. Another example within more like an infrastructural environment, let's say, is about parkings. This is an example I've been working on the last few weeks, so people among you that follow me on social media might have seen some pictures and some videos about this. And the idea of this script, of this workflow, is to evaluate a given site, and we have like a lot of freedom on that site. So we can choose where to place all of the main roads and the secondary roads. And I want to have, of course, a parking with the maximum number of parking spots. In most cases, it's very obvious. If you have like a rectangular shape, most of the cases, it's like take the longest edge, and that's with the edge that will define our parking rows, for instance. But now in this case, I want to do way more than just having a maximum amount of spots. I also want to have a good amount of spots which are accessible, so a little bit the larger spots. These are the blue ones, but also spots for instance, electrical vehicles. And actually, this parking space it's a huge area, and we want to have a good distribution of those spots for electrical vehicles. But at the same time, I don't want to spend too much money on the infrastructure for it. We want to concentrate them to one point so that our charging poles are close to each other. That could be a goal for it. Another goal in here is the payment terminals. I want those payment terminals to be distributed in such a way that people don't have to run like 10 minutes to pay their tickets. So reduce the walking distances. And another goal in here is having the maximum amount of green zones. I don't want to change this parking lot into like a bunch of concrete. No, I want it to still have some green zones in it, so to make the parking lot look nicer because it's within an urban area, and the people that are living around that parking lot want to have like a bit more comfortable feeling. So this is just some ideas that I put on a scratch pad. I was like, okay, what can we do with that? So it could even be like a parcel optimization. So it's not necessarily needs to be done on parking spots, as long as it uses those rectangles and places them along a linear line, and that's it. So again, before you start, you try to figure out what could be the workflow for it. So make a flow chart for this. And something new in this approach is that the script is using dictionaries within Dynamo. The exciting thing about dictionaries in here is that it's taking the data, it stores them into that dictionary, and then you can update the dictionary, your database, let's say, with new values. So for instance, you start with just a plain amount of parking spots. And then after evaluating the whole design, you can add, for instance, oh, okay, this parking spot should be converted into a parking spot for EV, so for electrical vehicles. Or this one could be replaced by accessible spots. And this dictionary, this database gets updated all the time with those new values until it gets like your solution at the end. So that's actually the approach that is used in here for doing that. So again, the workflow takes your data and constraints, in this case, again, from a Revit model. It's generating, analyzing, and ranking the solution until we get like a good layout. Now, in this case, the optimization is happening in a few steps. Because we have like a lot of variables, such as the variables for what is the position of the main road, what are the positions of the secondary roads, what is the position of each of these spots. These are lots of variables, and it can easily bring us to what we call the curse of overdimensionality. This curse is where you have like a huge amount of variables, and you want to optimize all of them. And you have like a huge amount of goals. And then you expect, like, if you click generate, that within 30 seconds you get your solution. And then 2 years later, you're still waiting for it and still didn't get a solution for it. So that's actually what might happen. So in some cases, it's good to start optimizing the first amount of variables, like the most important ones. What are the most important ones for this parking spot? Well, that's the position of the roads. First, we define the roads, and then we can see what we can do with the parking spots. Now, what I've done in here is actually first did a randomization of all of the layouts of the roads, and then selected one of the options from it, which tell me like, okay, this is a good solution. Aesthetically, it's good. It has a huge amount of parking spots, so I can select that one. And then you start optimizing for the other goals, the optimization of the number of EV spots and the position of the EV spots. And then another optimization is, when that is done, is the position of the payment terminals. Because the payment terminals and the EV spots, they depend on the rest of the layout. So it's not the EV spots that will define how the roads would be placed. You know? So that's actually that's a good example of how to deal with that curse of overdimensionality. Okay, let's go. Let's have a look on how that works. So again, on each script, as I told you, there's a lot of explanation inside of the script. So it's not like you will not find a huge handout of 200 pages. No, everything is within the script. So just open it up and have a look on it to understand how these things are working. So the first thing you normally do before you start working in a refinery is having a look how that script works. What happens if I drag my sliders in a random way? What happens if I combine this value with this value? Even if it's a very unlogical one, just test it. Because this will help you to avoid getting weird results or results that are even non-applicable. Always test it before you start. Now, as I also told you, use the colors for explaining your steps. So within the pink boxes in here, we get our results. This is where we use the evaluation part, where we use the ranking part of the process. The next step is where we want to generate all the options. Now, before you can use it in Refinery, you have to export it. So within Dynamo, you will find it. It's Refinery, export to Refinery, done. And then it saves your script onto a local folder, which is accessible from within Refinery. Now in here, the options that are generated is like, it's a bit of a cross-product option that you get in here. And I'm going to select the ones that are feasible, for instance, for this project. So I don't want to have like a straight main road. No, I want to have a main road that is connecting one side with the second side. So not like transversal throughout the whole environment. So we get like these 3 results. As you can see, the third result is empty. This means that it cannot be generated. Maybe the main road is like somewhere in the corner and the geometry cannot even handle the fillet on that polycurve. So that's why it's becoming empty, right? Now, it's not optimized in here. It's just selecting a layout for the main roads and for the secondary roads. And now that's where the rest of the optimization comes in. The optimization for the EV spots. So initially, all the EV spots are concentrated at the entrance. That's actually what our randomized solution came up with. And now I want to distribute those elements across the whole site and make it possible for having a good distribution of those EV spots. But also, I want to avoid that, for instance, multiple rows are only for EV spots. Because you as a user, as a driver, and driving a petrol car, you don't want to drive into a row where you cannot even park. So we want to have like a good distribution of it. And again, within the results representation in here, you can filter it. So I want to filter it according to, for instance, its distribution score. I told you like a scoring system is how we evaluate something. In this case, it's evaluating the distribution in such a way that if it's using all the rows, then it's a good solution. So I give it a maximum score. If it's only using the rows that are at the entrance or at the exit, then I give it a very low score. So this means that if Refinery goes through all the options and I say like maximize the distribution score for the EV spots, then it will aim to get the parameter values to have the distribution of the EV spots across the whole site. And this is the result you get. So instead of having it concentrated around that green arrow, now they are distributed across all the rows inside of that parking spot. And then the last optimization in there is the position of the payment terminals. The payment terminals in here, they are placed in such a way that we want to minimize the walking distance between every spot and that terminal, of course. And you see, there's a lot of goals. I'm unchecking them. Most people that want to test optimization are like, oh, let's check all of them and then run. And that's where you have to wait, and then yeah, you're blanking on your screen and then waiting for a long, long, long time. So don't do that. And then here, the payment terminal optimization is very easy. It's actually a simple part of it because it's just generating those little cylinders, those brown cylinders on several positions. It's looking if it's clashing with the secondary roads. If not, then it's a good solution. And then it's using the space analysis package to define the distance between each of the parking spots and its nearest payment terminal. And this is visualized with those green and red lines. So as you can see, the parking spots which are at the bottom right, they show up in red or with a red line, meaning that the walking distance is not optimal, meaning that I could change my script in such a way that the payment terminals are also allowed to be placed at the end of a secondary road, maybe. So in this case, they are only allowed along the main roads. So meaning that Refinery only can choose between those options, right? So within that kind of, within Refinery or within Dynamo, it will not look for it itself where it can place those payment terminals. No, you as a user have to define what are the boundaries for those terminals. Where can I place them? Along which line should I distribute them? And so on. Another advice that I could give you when you build those kinds of scripts is make them generic. Make them working on other sites as well. So don't fix on your current project. Try to use it on other projects. So the script in here was also built in this way that it can handle other sites. So instead of just a rectangle, it can also use a polygon for it. If it has 5 sides, 6 sides, or 7 sides, it doesn't matter. If it's a curved site, even that would work. So always think about that before you start building up your computational model. Another example is urban planning. As you could see, all the examples that we showcase within the architectural industry are mainly about layouting. It's always about placing elements onto a specific grid and evaluating it. That's because it's the most popular solution, actually, the most popular problem that can be solved with generative design. Now, in here, within this urban planning example, we are, again, using a specific context, which is a Revit environment. And this context is not only the site, but it's also trees that are on that site. So imagine that you have like a construction site with lots of old trees, and we want to save as much as possible of those trees when we create our design. So in this case, it's a bit different way of thinking. In here, we are thinking about placing buildings around the nature, and not like, let's kill the nature, build something on it, and then put some new nature in it. No, we are trying to save some of it. So this is, this could be your site, for instance. It's a fictive project, so it doesn't exist in here. But we want to take this part of it and have, again, a context which is very random. So the site perimeter is not like a fixed ideal geometry, No, it could be like a very specific, a very random geometry. And the result should be like a placement of a number of buildings where lots of things are taken into account. Not just the building size, but also its position towards that ellipse-shaped central square. We also want to evaluate, for instance, the number of green area we have in there. What is the number of trees that needs to be cut down to build it like this? And also, what is, for instance, the position of the building towards public transport? What is the position of each of the front doors of that building towards the plaza? So that people, if they come out of the building, they immediately see that central plaza, for instance. So all of these things are evaluated in the same script. So again, every time it's the same process. You take the input from Revit in this case, and we generate something from it. Now, the trick within this script was that it's again something where a lot of optimization is done. It's really multi-objective optimization we have in here. And the trick here is to, again, overcome that curse of overdimensionality and run the optimization multiple times. You have to run it maybe 4 times to get to your ideal result. First, optimize the position of the roads, then optimize the size of your building, taking into account, for instance, the distances to the public transport, distance to the central square, and so on. And then another optimization could be the building program. So each of the buildings, as you can see, has different colors. We have the blue, orange, and that other color that defines the program type of each of those levels. And that's actually something which is not influencing the position of your roads, right? It's not because of another grid definition of the central square with the road connection, which will define how the program type should look like. So that's why you do this optimization in two separate optimizations. First, the layout, secondary, the program type. Now in here, we limit it just to the layout of the buildings and the central square. And as you can see, the size of the central square is a fixed value, and everything is built around that square. Now, in some cases, you're not using the filters from the parallel system or from the 4D scatter diagram. You could also use the tables to just get values from it. That's also a way of sorting your designs in here. Now, another step is, of course, integrating it into your design model, meaning that from within Refinery, you select your solution, transfer it to Dynamo, and then from Dynamo, you can transfer it back to Revit to document the ID that came out of the optimization. So if we go through that design technology progression, we started with the computer-aided drafting, right? I skipped sketching from this because, as I told, I assume that none of you is at that stage. So we have computer-aided drafting, there's parametric modeling, design automation, and computational modeling. All of that is within traditional and parametric design, meaning that we use that to record a decision in a traditional design, and we use parametric design to associate geometry with that decision. But the thing is that within everything within the blue area, we document an ID. It means that if I say, like, let's design a chair, that's the ID. And you already have that chair in your mind, right? But that's the approach you use in traditional and parametric design. Let's design a chair. At the other hand, if we go to generative design in the green area, the approach is completely different. It's not about designing a chair anymore, it's about design something to sit on. And generally, it can be a pillow, it can be a couch, it can be a bench, it can be like this nice sitting cubes. So it's not a chair anymore. You're not limiting your ID, you're actually expanding the number of options you can have to solve the challenge of having something to sit on. That's the mindset you should have when you want to get into generative design. Not just saying, like, let's design a building. No, let's design something which is meeting this goal, the other goal, which is within that boundary, which is within those constraints. That's how you can approach your designs with generative design. Now, and the moment you are in the phase of computational modeling, you're very close, actually, to generative design. That's why, actually, these colors are gradually going into each other, that green and blue. So the moment you're at that stage, actually, the threshold to get into generative design is very low. It's just running your script within Refinery, right? But keep in mind, it's about analyzing and ranking your designs. That's the most difficult part. And that's something you cannot just learn from within a manual or within a training. It's something you have to learn by approaching your designs from a different way and change your mindset and your process on it. Now, for people who are already at the end of that design progression, you're like, oh yeah, I'm already doing generative design for months, for years. What is the next step for me? Well, that could be machine learning. Machine learning is something which is coming up. We already have it within Autodesk. We invested already in that area with BIM 360 Construction IQ. And more will come definitely within the AEC industry when it comes to generative design combined with machine learning. I already saw examples from people that are using sensor technology to measure data from designs that have been made with generative design methodologies, and then use the sensor data to make your algorithms smarter, to feed them into your Dynamo script and make them smarter. And this is how it happens. You can also use virtual reality, for instance, to document the idea that comes out of a generative design solution. So, what level of design? I'm not asking you to tell me at what stage you are, but keep it in mind for yourself. Where am I now? You know what to do to get further and to progress into that design technology. And I can only say to use those examples, to go through each of the examples that I've placed online and go through them, learn from it, and try to do it yourself as well. And try to think about maybe other applications to use those same examples on. Now, if you want more of this, there is the Refinery Primer. I really would like to encourage you to go on it and have a look on the primer. It's a really nice thing. It's explaining in very easy language what is generative design and how you can apply it. There are lots of more examples in there, and it's still developed, this primer, and there will be way more examples in there. So definitely check it out. Go on it, have a look, give feedback on it to the people that built this. And this might help us to have like an easier access to generative design and to understand it better. So we are at the end of this first class at AU, and before you guys leave, I would appreciate if you open up the AU app and give some feedback if you liked the class or if you didn't. It's always good to know how we did on these kinds of things. And then we still have like 10 minutes to do some Q&A. So, and people among you who have questions, I would like to encourage you to come over here to the microphone because it's recorded and we want to, other people that are watching online, they want to hear the question. So feel free, come on to the microphone and ask your question. I know it's a big step to come to the microphone. Hi there.
My question is, so when you build the Dynamo script, does Refinery take any Dynamo script, or you have to place certain nodes for the Refine to analyze?
Yeah. So Refinery is accepting input nodes, and input nodes are, for instance, sliders, so things that can vary. If you have like a number node, then a number node is a constant value, so it cannot vary. So it needs to be a slider for your inputs. Within the Dynamo context, you can right-click on one of those nodes and say, like, this is an input. At the other side, for your objectives, for your goals, it needs to be a watch node, and you give a name to that watch node. Actually, every node that is used within Refinery should have a name. So if you double-click on that node, you can give it a name, and then it will pop up as the variable name inside of Refinery, or as the objective name for the watch node. Okay? Yep.
Hello. I'd like to clarify my understanding of the dictionaries you mentioned in the middle of the presentation. Is that a way to automate? You mentioned not to analyze multi-factor at one time because you get paralysis by analysis and run too many iterations. Are the dictionaries a way to do that, saving, for instance, the main road layout in the parking lot and then step into EV optimization or something else?
Well, actually, the dictionaries are used for combining geometry with data in a structured way. So instead of having to create like 10 lists, one with geometry, one with data A, one with data B, and so on, you can store it inside of that one dictionary and then extract specific values from that dictionary to process them further. So that's actually what it does. It's like a table with values, and they are not exposed to the geometrical environment. So sometimes if you have like a huge computational models with a lot of geometry, it slows down the performance, the graphical performance. With dictionaries, you don't have that because it doesn't show the geometry. It only shows it when you extract the geometry from it.
So it's caching results, so you don't have to go back and read.
Exactly.
Okay,
Yeah.
Thank you.
Hi.
Hi.
When you were talking about the liquor store, you were saying that you're expecting more to come from that. You guys are developing more on that process, and I was wondering if you know what that evolution of that process looks like.
No, it's actually the customer that is more developing on that specific part. It's not Autodesk doing anything. Well, we support them, we help them to give advice on how to evolve on it, but they internally within their innovation team, they are looking to expand this example and to make it more complex, more advanced, not more complex, but more advanced.
Thank you.
Yep. Hi there.
So I've tried with the refinery with several tasks, and my question is for the outputs, can we set weight for them? I mean, if we consider one output is more important than others, so can we set different weight to the output to get the best?
Well, a good trick for that is actually when you have, for instance, output A and output B, you create an output C that combines A and B in a weighted shape. That means that, for instance, if output A is more important than output B, and both of them need to be minimized, you can say, or maximized, you could say like, okay, take output A, do this 1 times 3 plus output B, and this is my output C. So if you start Refinery running in such a way that it needs to maximize C, then it will automatically go in such a way that A and B are combined, but A will be more important than B.
Thank you.
Yeah?
So we've seen a lot of good examples of the use of or application of generative design on design conceptualization, but is there any promise for this application on design documentation as well? Like say, give me an elevation of every interior wall face in my building?
Give me every level of, for instance?
Like if I'm starting with a new project that I've never done before, and I just want to generate a sheet set. Is there a promise for generative design to address that need?
Well, the thing is, what would be your objective? Because if you apply generative design, you need to have an objective. It's like, do you want to maximize the sheet sets or minimize them? Or is it more like, I want to automate the generation of the sheet sets? So, yeah. Yeah?
Yeah, it could be all of those.
Yeah, well, for now, the documentation part is actually more within design automation. It's like doing these time-consuming tasks in the shortest time. So, for instance, the creation of documentation sheets in such a way that, for instance, takes an Excel file which has all the numbers or maybe the disciplines to combine a sheet number, for instance, and then with Dynamo you can automate the generation of all of it. But within generative design, if you would need to use generative design for it, it's generative design on data, because a sheet is actually data. It's just mirroring what is in your model, and it's showing it in a digital way. It could be in shapes or it could be in data. But in generative design, yeah, optimizing data means that you need to evaluate them and you need to rank them and to achieve a specific goal. And I think that's a difficult part where what could be the objective of that documentation part, for instance.
Okay.
I think that's the biggest question in there. Sorry, I'm giving you an answer with a new question instead of answering your question. Any more questions? Yeah, one more.
Hello. My question would be probably mostly related to that office tower example.
Mm-hmm.
Now, there's certain aspects you have optimized or you try to optimize, like facade area or floor area and so on. Now, do you see somewhere a limit what you can do with the technology in terms of, can I bring in things like energy analysis, wind analysis, structural optimization of the building? I mean, there's so many aspects that would influence the optimal shape. Where do you see the kind of currently the end of?
Actually, there is no limit.
Okay.
Everything you mentioned, the answer is yes, 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 yes. All of it, you can do this. The only limitation there might be is the availability of software for it, or the availability of packages for it. Like in structural analysis at this moment, robot structural analysis is not connecting with Refinery yet. The reason for that is because Refinery opens up Dynamo in a separate environment, and it's only Dynamo. So nothing else, not even Revit or Advanced Steel, can be opened at that same time. So that's a limitation, but this is more a limitation that can be overcome by developing, and that's something we're working on. But when it comes to energy analysis, there is the solar analysis package, for instance. This can be used perfectly within these kinds of workflows. People can also make their own analysis algorithms by using Python maybe, or by using the out-of-the-box nodes and combine them in a new package, or in your own custom node within the company. Or if you are even more advanced, you could use zero-touch nodes to make your whole complete advanced analysis on the design. So Dynamo is actually a good platform to evaluate the geometries that are generated based on that external content, for instance, or external inputs from Revit, a site, for instance, or whatever you want to bring in into Dynamo. So that's the limitation. Yeah, I always say, like, you can solve 99% of the problems with it. And then it's the other things that cannot be solved is covered by that 1%.
Would you need to run those things separately, or would you do that separately? Let's say solar analysis, wind analysis, or something.
Well, yeah, that's actually, again, where you come into that curse of overdimensionality. So sometimes it's like, yeah, what is most important? Is it first the wind that should be analyzed, and then we have a look at the energy? Or is the combination of both really defining how our building will look like? If it's the second answer, then yes, you have to combine them into the same script. If it doesn't influence each other, then it's better to have it separately running. It can even be done in one and the same script if you want, and then use you can uncheck in Refinery which outputs you want to optimize, and then they will be ignored, so that it's still optimizing towards energy analysis, and then at the same time you get, for instance, results for the wind analysis, which can be used to filter, for instance. Or you can do a second optimization afterwards. Okay? Yep. Okay, perfect. So this brings us to the end of this presentation. And yeah, I think we still have like half an hour to run to the main stage for the keynote. So thank you for attending this session, and also for the people online, thanking you for being here with us, and enjoy the rest of AU.